Our Sun is a very dynamic star, and it's emitting mass at a constant rate. This creates the solar wind. Solar phenomena taking place at the solar surface influence the speed and density with which this mass is emitted. Because our Sun is rotating, this results in a spiral-like solar wind structure, very similar to the spiral you get when you spray a water hose in one direction and then start turning. Typical solar wind speed values are 250 to 650 kilometers per second. Sometimes the magnetic field that is inside the Sun pops out of the solar surface and creates loops in which mass is trapped. Magnetic instabilities can trigger a release of a large eruption of mass at very high speeds. These large eruptions are called coronal mass ejections, or for short CMEs. Typical CME speeds are 400 to 1500 km per second. This means that on average, a CME directed towards Earth arrives within about 3 days. The solar wind, together with CMEs and other solar phenomena, create what scientists call space weather. Because CMEs contain an internal magnetic field, they can have a very high influence once they arrive at Earth. The interaction between the CME and our Earth's magnetic field can produce a wide variety of effects. The most beautiful effect is the aurora. Other effects, however, may impact our daily life more drastically. For example, damage to satellites, problems with telecommunication and navigation systems, disruption of airplane communication, and even large power outages. Therefore, it is important that we can predict the arrival of such a space weather storm so that we can prepare our satellites and electricity nets accordingly. Observations are an important tool for this goal. However, they are sometimes very limited or difficult to interpret. Think about projection effects because we observe only in 2D. Another example is that the magnetic field in a CME is impossible to observe. Therefore, we are in need of mathematical models that can provide more insight. To predict and forecast the arrival of CMEs, we are using a mathematical model called EUHFORIA. Our model solves the magnetohydrodynamics equations, which combine hydrodynamics and Maxwell's equations, and describe how a conductive fluid interacts with an ambient magnetic field. This yields a model that can realistically simulate the solar wind from very close to the Sun up to the Earth and beyond. Superposed on a solar wind, we can also inject CMEs at the inner boundary of our model. This allows to simulate how the CMEs that are ejected from the Sun propagate toward Earth. Our model forecasters typically have the following visualization to provide them with the necessary information on the solar background wind and the CME propagation. On the left panel, we have a top view of the ecliptic plane. This is the plane in which the Earth is rotating around the Sun. In our coordinate system, the Earth is always at the same position, 0 longitude. On the right side panel, we show the central meridional plane. This is the plane perpendicular on the ecliptic plane and passing through Earth. Here we are plotting the radial speed of the solar wind in a color contour plot. On the bottom panel, we show what we call a time series. It shows us how the radial speed is changing in time at the position of Earth. In red, we show observations from the ACE spacecraft. In blue, we show synthetic data resulting from the simulation model. Now that we have mathematically modeled the solar background wind, we want to simulate the evolution and impact of some CMEs. Before we can simulate the propagation of CMEs, we need to determine the initial properties of the CME. These include the angular width of the CME as well as the initial speed of the CME. We can do this by using coronagraph observations. Coronagraphs block the bright light from the Sun so that we can see the solar wind as well as solar phenomena such as coronal mass ejections. Once we have determined the width and speed of the CME, in addition to its longitude, latitude, and the time it occurred, we are ready to start with simulating the CMEs. We have developed different CME models. Let's start with the simplest model that space weather scientists have been using for the past decade, the cone model. The cone model is a very simple model. It is pushing a sphere through the inner boundary. The sphere is modeled as a density and pressure enhancement. Here you can see a simulation where we are modeling a total of 5 successive CMEs. One large drawback about the cone model is that it does not have an internal magnetic field. Yet, this plays a key role in its interaction with the magnetized solar wind, and it's crucial to determine how it interacts with the Earth's magnetic field. Therefore, ideally, we want to have a CME model that takes into account this internal magnetic field. For this, we are using a so-called magnetic flux rope model. When observing a CME before its eruption, we usually find a twisted magnetic flux rope. Its structure looks something like this. We have chosen to implement an analytic self-similar flux rope model, as this allows for easier implementation and faster computation, and our computation time for forecasting CME's arrival and impact is very limited. In this simulation, we have replaced one cone model CME with a flux rope CME. We can clearly see from the timelines at Earth that the magnetic field is poorly modeled by the cone model. The flux rope model, however, can capture more of the features of the magnetic field structure of the CME. Let's enjoy the beauty of CMEs one last time.